Hello and welcome. I am Beth Mashesky, Senior Scientific Specialist at the Illinois Sustainable Technology Center, which is part of the Prairie Research Institute at the University of Illinois. A few housekeeping items before we get started. You can download the slides in the handout section of the GoToWebinar toolbar. Today's webinar is being recorded. The recording and slides will be available for viewing online in about a week. I'll be sending out an email to everyone who registered for the webinar once those are available. Everyone will remain muted for the entire webinar. You can type in your questions through the GoToWebinar toolbar, and I'll be reading those to the speaker at the end. So with that, I'm very pleased to welcome today's speaker, Dr. Kit Windows-Yule. Kit is an assistant professor in the School of Chemical Engineering at the University of Birmingham in the UK. He earned his PhD in nuclear physics at the University of Birmingham. Before his current position at the University of Birmingham, he worked as a researcher in mechanical engineering at a university in the Netherlands and in chemical and bioengineering at a university in Germany. His current research focuses on addressing climate change through novel plastic and heavy metals recycling techniques and advancement and optimization of industrial biofuels production processes. His research also focuses on optimizing industrial process equipment while working with numerous industrial partners and developing novel position imaging methodologies. So Kit, thank you for joining us. The webinar is yours.
Thank you very much, and thank you for having me. So my slight mouthful of a title today is Advanced Positron Imaging of Plastics in Fluidized Beds Toward a Circular Economy for Plastics. Hopefully in this particular institute you'll all be very aware of the importance of a circular economy for plastics, given that plastic pollution is one of the great challenges facing society today. Positron imaging perhaps a bit less familiar with, but that's something that I'll introduce to you as we go along. So before we start, I want to try a little word association exercise to get everybody thinking. And the question I'm going to ask is, what word springs to mind when you think about the word plastics? What I'd like you to do, what I'd like you to do is go to www.menti.com and enter the code that you can see there on your screen. And all I want you to do when you're there is to type in as many words as you can think of that spring to mind when you hear the word plastic. And the idea for this is to get a gauge of what people's opinions are on plastics and the related matters. So when you get the chance, go to the website, enter the code, and type in anything that springs to mind. There's no right or wrong answers with this. Waste, okay, I think judging by the title of this talk, that's quite a good answer, and you can include as many as you like. I think everybody can put in a good for water bottle. Okay, what else have we got? Pollution, water pollution, Lego, okay, a bit more of a positive association there. Please keep them coming. Ubiquitous, absolutely. Micro, waste, a lot of people saying water pollution and water bottles. So the larger the words are, that means the more people have actually said them. So we've got water bottle, water pollution, waste, ubiquitous, polymers, oil, artificial. Brilliant, some really interesting things here. But the one that's the biggest here seems to be water pollution. The second biggest, ubiquitous, water bottle and waste. Okay, this is very, very interesting. So what we immediately see there, we go back to my presentation in a second, is a lot of negative associations when we talk about plastics, waste, pollution, people picturing water bottles being strewn on the street. And it's a very interesting thing, because one of the questions I want to ask at the start of this talk, which may seem a bit odd for a talk that's all about plastic recycling, but it'll make sense in a bit, is that the idea of eliminating plastics, getting rid of single-use plastics, is a very big thing at the moment. But people don't often enough stop to ask themselves whether or not this is actually an achievable goal. And more importantly, even if it's achievable, even if we can get rid of single-use plastics, is it a sensible goal? And what I'm trying to say here is that we need perhaps a more nuanced answer to this question. If you ask, can the use of plastics be reduced in certain areas, then the answer is absolutely yes. The question, should the use of plastics be eliminated in all areas, is the one that the media seems to want to ask. And the answer to that is a lot less straightforward. And the reason for this is, oddly for somebody whose research career depends on trying to address plastic pollution, I actually really do love plastics. They are an extraordinary material. They're lightweight, they're durable, they're easy to produce, they're cheap to produce, they're cheap to use. And the simple fact of the matter is, in a very real sense, they can't easily be replaced without some kind of trade-off. And in some cases, this trade-off can actually outweigh the benefits of eliminating plastics. So things like, if you're trying to transport something, if you're trying to transport, say, glass bottles instead of plastic bottles, which is something I'll talk about in more detail in a second, then obviously you've got to consider increased transport costs. Similarly, if you go for other materials like paper instead of plastic, you've got decreased functionality and decreased reusability. If you stop using plastics to protect food, then you're going to increase food waste. If you start using more fragile objects, then you can increase losses. And if you go back to materials like aluminium and steel instead of carbon fiber composites and plastics, then you risk decreased efficiency. To take a look at one of these in a little bit more detail, if we think about increased food waste, there's a few startling statistics that I came across while I was, for the first time, researching plastic waste. The first one is that here in the EU, we waste 20% of all the food we produce, which is per person 173 kilos each year. So in other words, in a given year, the average person produces twice their own body weight in food waste. In a year globally, this adds up to 1.3 billion tons at a cost of $1 trillion. And amazingly, the carbon footprint of food waste in the UK is actually 3 times higher than that of plastic waste. It uses up 25% of the world's water supply just growing food that is never eaten. And one thing that people say to me a lot is that you've probably all heard this, but fruit and veg have their own natural protection. We don't need to wrap fruit and veg in plastic. And while that may be true in some cases, if you think about something like a cucumber, even though it's already got its own skin on, it's got its own natural protection. If we use just 1.5 grams of plastic, we can extend its shelf life by about 14 days. So if we look at increased food waste, we see that plastics are not the only trouble here. And similarly, if we look, a brilliant example was briefly in the UK when Coca-Cola decided to be eco-friendly and replace their plastic bottles with glass bottles to be more environmentally friendly, which was an absolute disaster. And the reason for that was that if you are producing glass instead of plastic, your raw materials costs skyrocket, your energy usage goes up, then you have increased transport costs because the plastics are lighter than the glass. You have increased waste, both during transport and during usage. And then once we've finished with it at home, we've got to transport it back to a recycling plant, which again is a higher fuel usage than plain plastics. Again, when we reprocess it, an increased energy usage and still more fuel usage when we take the feedstocks back to the factory. And the amazing thing about this is, in the case of glass bottles versus plastic bottles, it can actually be more environmentally friendly to use and discard plastics than it is to actually recycle the equivalent amount of glass. But the question here is, what if it wasn't an either or? What if it wasn't recycle glass or throw away plastic? What if we could actually recycle the plastics? And that's the point here that I'm trying to get across, is that removing plastic is not the solution to our problem. The solution to our problem is recycling plastic, and that's the area that I'm interested in. So the question that worryingly springs to some people's minds when I give that piece of the talk is, so that means that plastic's absolutely fine, it's not a problem. It may not be the problem, but it is still a huge problem. Every year globally, we produce 400 million tons of waste plastic. And that's equivalent to, I mean, because 400 million tons is quite a hard figure to get your head around. Once you get into these really big numbers, it's quite hard to actually conceive what that means. But every year and a half, we're producing in plastic waste an equivalent mass to the entire human population of the Earth, every year and a half. And of this vast amount of plastic, 91% of it is not actually recycled. Even more concerningly, of the 9% that we do recycle, the most isn't actually going back to make high quality products, it's actually being downcycled to make lower quality second life products. And what I mean here is that when we hear about plastic recycling, what most of us think of intuitively is we take a nice plastic bottle like this, we send it to a recycling center, and we get back another nice, clean plastic bottle. In reality, this kind of recycling is this kind of mechanical recycling doesn't actually reproduce a nice, clean plastic bottle. What actually happens, we send it to a mechanical recycling center, and it's actually, because the stuff they get is impure, it's mixed plastics, it's got biological elements in it, they can't make it back into a food grade bottle. So instead they downcycle it into something like a black plastic bag or a carpet. And then when that carpet gets to the end of its usable life, it's already such low quality material that we just end up throwing it away anyway. So what I'm trying to say here is that a lot of the conventional recycling we do these days is not actually recycling at all. It's basically just delaying landfill. So the question is there a better way to do this? Is there a way we can take our plastic bottle and instead of turning it into a carpet, we can turn it back into useful plastic feedstocks and back into useful virgin quality products? And how we can practically achieve this. So the chemists and the chemical engineers in the audience will be shouting in their heads, pyrolysis, of course, you can pyrolyze this waste plastic. And you are absolutely right. So the main focus of this talk, the main focus of my research at the moment, is working with a company in the UK called Recycling Technologies, who have designed this fantastic piece of machinery, which in essence takes in mixed plastic waste, the key there being mixed. It doesn't have to be absolutely separated out from one another. It can handle all kinds of plastics bundled up together. And it converts this plastic waste into valuable petrochemical feedstocks and fuels. And the way it works, if I walk you through this diagram quickly, the main heart of this process are these two fluidized bed systems here. Okay, we've got this one called the regenerator, which heats up some sand-like particles to about 800 degrees, and then pumps them through to this second unit, which is also a fluidized bed, hence my focus on fluidized beds in this talk. And by now they're about 600 degrees, and we pump our waste plastics into this system. Now, as any of the chemistry-minded people around here will know, if you're heating plastics up to about 600 degrees in an oxygen-free environment, you're going to get pyrolysis. So the long-chain hydrocarbons that make up our plastic are being cracked, they're being split down into their smaller constituents, and then the resultant gas is pumped out of the system, it's refined, and it's distilled into lots of different fractions, of which we have some nice low-sulfur fuels, we have some plastic feedstocks, and we also have light hydrocarbon gases. Because these light hydrocarbon gases are difficult to compress down and sell on, what we do instead is we actually pump them back round to our regenerator, and we then burn them to heat up the sand. So this whole system is quite impressively self-sustaining on the products that it actually produces. So what we have here, by utilizing this fluidized bed technology, we can allow large-scale processing. And even more impressively, and the key to this technology is that it has a modular design. So you'll notice that each of the main units here is encased in a sort of iso frame. And what that means is that we can split this system apart, we can load it onto a series of flatbed trucks, and we can drive it to anywhere that it's needed and install it very, very easily. So the benefits of this modular design, it means firstly that it's very easy and efficient to set up new plants. And that in turn means that instead of having big centralized plants at one place or two places in a country and having to transport our plastics miles and miles and miles, you can set up one of these machines in every local council area. Then the waste can be efficiently transported and turned back into plastic feedstocks on site and used again very easily, which of course minimizes both transport costs and the associated environmental costs. The second reason this modular design is so important is that you implement it with relatively little infrastructure, which is obviously extremely good news for third world developing countries where the plastic waste crisis is the most prominent. So this technology, it's obviously extremely impressive, and listening to it like that, you might think, well, why on earth haven't we rolled this out and solved the plastic waste crisis already? It's a proven concept, but unfortunately, it's still a long way from being a commercial reality. And the simple fact underlying that is that the hydrodynamics of these reactors that I explained to you in the previous slide, we simply don't understand them. And if we don't understand them, it means that we can't optimize this system. And if we can't optimize this system, it means we can't make it cost effective and efficient enough to actually make it attractive to the kind of people who need to use it. The real big problem we have, the reason that these hydrodynamics of this system are not fully understood, is that this is the real system. This is what it looks like when it's not in the form of a cartoon. Okay, so it's a large opaque system. It's very hard to tell what's going on. I gave a similar presentation to this to a group of young students starting out at Birmingham University recently. And I said to them, well, I asked the question, how can we improve our knowledge of these systems? And they said, X-ray vision. They said you should use X-ray vision to see inside it. Now, of course, that's an absolutely stupid idea, because X-rays would go nowhere near penetrating that thick stainless steel exterior. What you actually need is gamma ray vision. And as luck would have it, at the University of Birmingham, we do have gamma ray vision, or more specifically, what we have is Positron Emission Particle Tracking, or PEPT. And that's a technique that was developed at the University of Birmingham, and today Birmingham still houses one of only 2 PEPT facilities in the world. And what PEPT allows us to do is it harnesses highly penetrating high energy gamma radiation that lets us actually penetrate the steel exteriors of these systems, penetrate the dense opaque materials within, and actually see inside and actually reproduce the hydrodynamics of these systems. So before I go any further, I want to give you, for those who aren't familiar with the technique, a brief introduction to positron emission particle tracking and how it actually works. I'm not going to delve too deeply into the nuclear physics of it, because I don't think that's what everybody came for. So I'll just give a brief overview. So if we consider this as a very simplistic model of our fluidized bed, now what we can do is we can take one of the particles from this system, one single grain of sand, and we can make this grain of sand radioactive. We can label it with a radioisotope that emits positrons. Now those who listen to their physics A levels will know that when a positron hits an electron, it will spit out a pair of gamma rays whose trajectories are antiparallel and collinear. To put that more simply, it means they form a straight line. And since we know that they form a straight line, if we can detect each one of these gamma rays, then we can reconstruct the path that we know it must have followed. And if we can reconstruct this path enough times, and we know that all these paths have to go through our tracer particle, then we can actually locate where our tracer particle is. And when we do this, we use highly active tracers. So we're talking around 10 to 100 megabecquerel. So they're spitting out tens or hundreds of millions of these gamma rays every second. And that means we can locate this particle hundreds or even thousands of times a second. And we can watch what it does and where it goes within our system. So what we have here, we have a fluidized bed, and then we have what's going on inside this fluidized bed. We have the blue tracer representing a single plastic particle and a red tracer representing a single sand particle. Now you may say to yourself, well, that's all well and good, it looks very interesting, you can track a single particle and see what it does, but what use is that? Well, the answer is, because a system like our fluidized bed is ergodic, we can take the long time average of these particles' behaviors and use them to actually infer a huge amount of information about the full ensemble dynamics of our system. So for instance, we can plot out its three-dimensional velocity vector fields, we can actually visualize the flow within our system. Even more importantly, for the current piece of work, we can actually plot where within the system our plastics are most likely to be. And so in this particular example for this system, what we see is our plastics all tend to accumulate near the top of the system, and they don't really like to go near the bottom of the system. Now, if you're thinking about the process that we're trying to induce here, if you're thinking about pyrolysis, having a very uneven distribution of particles is not something you want. So we need to actually look into ways of improving this. Now, obviously, that's just a very simple model system, but PEPT can also handle some much more serious equipment. So this is actually a slightly scaled down pilot plant that was provided to us by our industrial partners, Recycling Technologies. And PEPT can even see inside this big, solid kind of industrial level equipment with relative ease. So what can PEPT tell us? Well, we've seen that it can show us solids fraction distributions, it can show us residence times distributions, it can show us three-dimensional velocity distributions, velocity vector fields, it can show us velocity PDFs, it can show us the granular temperature, so a measure of the turbulence within the system. It can allow us, if we've got binary or polydispersed systems like the ones that we're using at the moment, it can tell us, is there one area that's more occupied by one species, say our plastic, and another that's more occupied by another species, say our sand, and important questions like that. We can look at diffusion, we can look at dispersion, we can look at mixing, we can look at bed turnover rates. We can extract a huge amount of information from our system. And for that reason, positron emission particle tracking has allowed us to gain a real insight into the dynamics of these systems. So that's PEPT, and those are the systems that we're looking at. So the last part of this talk, and perhaps the most important, what have we managed to glean from these systems using our positron emission particle tracking? Well, the first and one of the most striking observations that we made was before Recycling Technologies had access to PEPT, the way they designed their systems was through empirical modelling. Now, when we actually decided to look at what they were modelling, the transport disengagement height of the fluidized bed, and compare it to the values we could actually directly measure with PEPT, it became immediately apparent that the model the company were using, represented by this dashed line here, was nowhere near the actual TDH represented by our symbols, our crosses, and our circles here. So in other words, the models that the company were using to design their equipment were terrifyingly far from the truth. And more importantly, we looked at basically every relevant TDH prediction equation that we could find, and almost none of them came close to the actual behavior, and none of them at all managed to fully capture the behavior of our systems. And so obviously this is telling us very clearly that the way we are designing these fluidized bed systems at the moment is not working, and we need something like PEPT to actually visualize the interior dynamics in more detail so that we can finally understand what's actually going on, not just what these apparently flawed equations are telling us is going on. So the goals of the project were firstly to ensure that we've got even mixing between plastics and bed material. Because if you're trying to produce a nice end product through pyrolysis, you need to make sure that there's even heat transfer between the different elements so that you've got an even temperature. Because of course, if you've got uneven temperatures within your system, then that means you're going to get different pyrolysis products. If you can't control the products of the pyrolysis, then what you're getting out the other end is not going to be what the person buying this product is wanting. We also wanted to make sure that we ensure efficient dynamics and desirable flow patterns and an absence of dead zones or defluidized regions within this system. Because obviously, if the system itself is wasteful and inefficient, then it's not really doing its job in terms of trying to save the environment. And finally, of course, identifying any design issues. How do the current designs fare? How can we improve any shortcomings that they might have? Okay, so in the last sort of 10 minutes of this talk, I'm just going to give a very brief flying overview of the work that we've done. But of course, at the end, I'm more than happy to answer any questions anybody had and to delve into any one of these individual projects in a little bit more detail. So the first thing we decided to look at, as those of you who are familiar with fluidized beds will know, one of the key aspects of a fluidized bed is the distributor. For those who are unfamiliar, the distributor is basically the thing at the bottom of a fluidized bed through which we pump air that actually causes the bed to move around in a fluid-like manner. If you don't design your distributor well, then you get a suboptimal flow regime. So to put it briefly, if you're designing a fluidized bed, you want either this type of flow, or you want this type of flow. You don't want A or D, okay? A suboptimal flow regime is inefficient. The other thing we don't want is dead zones or defluidized regions, because this obviously means poor mixing. Now, all of these things we can directly infer from our three-dimensional PEPT measurements. So we can see the dead zones in the system are highlighted as these blank regions of this occupancy plot. You can see the flow pattern illustrated by the directions of the arrows flowing around our system. And you can also see regions of poor mixing where we have very blue or very yellow parts of the system. So from these simple plots that we produce using PEPT, you can see that as we increase the number of orifices in our distributor, we get smaller and smaller and smaller dead zones, and our mixing gets better and better and better. Okay, so these are just some of the things that we can envisage going on within our system. And the way we conducted this study to look at the effect of distributor design, we created a series of distributor plates that systematically varied the size of the orifices. Again, for those unfamiliar with a distributor plate, these are the holes through which air is pumped. So we've changed the size of them, we've changed the number of them, and we've changed the way in which they are spaced. And then we use PEPT to take some information from these systems, and we derive a set of indices, one of which measured the quality of the mixing between the bed material and the plastics, and the other of which told us how much defluidization there was, how big the dead zones were within these systems. And by plotting these nice scalar indices, we can tell how much each one of these factors had an influence on the behavior of our fluidized bed. So if we look first at what we defined as our distribution index, it's simply a scalar measure of how well mixed the system is. A very high distribution index means that it's not very well mixed at all. A very low distribution index means it's exceptionally well mixed. And what we found was, as you increase the number of orifices, you get a very clear downward trend. The more holes you have in your distributor plate, the better your mixing. We found a weak but interestingly non-monotonic dependence on the diameter of the orifices, which is actually a very interesting finding, because it's widely assumed that smaller diameters would lead to a larger pressure drop and therefore better mixing. What our results implied is there may actually be an optimal diameter for these orifices to cause maximum mixing. And finally, and perhaps most interestingly, we found that the position, the pattern in which we put these holes has almost no obvious impact on the behavior of the system. We then repeated this analysis, but instead of looking at the quality of the mixing, we looked at the amount of defluidization within the system. And again, we found a strong monotonic dependence on the number of holes in the system. More orifices means a smaller dead volume. We found a non-monotonic dependence on the position, and we found a very weak dependence on the diameter of orifices, which again is a very interesting result, because it's quite unexpected that changing the size of the holes through which you push this air has very little effect on how much fluidization you experience. Now, even with a very good design, and this was another interesting thing we found from the more industrial point of view, that even with a distributor that normally works extremely well and produces a nice double roll pattern like we see here, if just a couple of the nozzles in this distributor become blocked, then it can very negatively impact our flow, and we end up with something that looks like this mess over here, which again is obviously not ideal for trying to produce this pyrolysis process. So we've got ongoing work now to try and build more resilience into these distributor networks. How can we design them so that even if something goes a little bit wrong during the process, it doesn't disrupt our system entirely? And if we do get them right, our results also seem to show that no matter how hard we excite this system, we always have these nice, regular, two-rolled patterns. The problem, of course, is that just having a nice, regular flow pattern doesn't necessarily mean you're getting good mixing. Okay, so what we have here is each one of these plots represents a different system at some particular plastic fraction and some particular flow rate. The blue lines here represent distributions of our plastics, and the black lines represent the distributions of our fluidization medium, our sand. Now, in the case of perfect mixing, these lines should be absolutely identical, and if you've got strong segregation, then you will see that one of these lines don't actually line up with one another at all. And what we found is, this was not a particularly surprising fact, but it was a very interesting one, that as we increase the flow rate, we get better mixing, and as we reduce the plastic fraction within the system, as we have a greater ratio of sand to plastic, we also increase the mixing. And the trouble with this is it means that maximizing the efficiency of our system is somewhat of a balancing act. Because if we want to produce good quality products, then we want to make sure that we have the best possible mixing. But the problem is the best possible mixing is at the highest flow rate, which will burn up a lot of energy, and the lowest packing fraction, which will massively impact the amount of plastic you can process per hour. So trying to actually get this system as a whole working at maximum efficiency is a careful balancing act. Another interesting area that we looked at was we're moving away from trying to change the design of the fluidized bed system itself and looking instead at the products, the plastic waste particles that we're putting in it. One of the most energy wasting parts of any of these pyrolysis processes is actually grinding up the initial plastic waste to get a uniform size and a uniform geometry. And the question that the company put to us was, how much does it actually matter if all these particles are all the same size? In other words, how much time and energy do we have to waste trying to get a uniform geometry in these plastic pellets that we're feeding into our system? So what we did, we 3D printed a range of different types of particles. We kept their volume constant, so they've all got the same volume and the same mass, but their shapes strongly vary. So the aspect ratio of these shapes varies by about 2 orders of magnitude. And the really interesting result we saw from this is that as we vary the gas flow rate into our system, or as we vary the bed height, we see a very strong influence on the way that these plastics become distributed within our system. But if you look at how, for any one given plot, species 1, 2, 3, and 4 differ, the answer is not very much at all. So in other words, the shape of the plastics that we put in there has almost no impact on their mixing quality within the system, which, although perhaps a slightly dull result, is an incredibly positive one, because it means that we don't have to expend huge amounts of energy pre-processing these plastics, so we can actually make this process much more efficient by removing a couple of steps right at the start. And that's exactly the kind of result that we're after. So that was a very brief flying tour of the research that we are doing at the moment. To summarize, we're working with a very promising new plastic recycling technology, and we're using positron emission particle tracking to actually see inside these systems and gain a much deeper understanding of their internal processes than is possible using conventional techniques. The end goal being that we can optimize the design of these systems so that ultimately they become a commercial reality. We can roll them out into the big wide world and actually use them to take a serious step towards addressing the plastic waste crisis. As for the more specific results, we've looked into the mixing within these systems, which is of course vital to ensure the efficiency of the systems, but also to make sure that the product we get out at the end is as good as possible. We found it's very, very strongly dependent on the gas velocity, the plastic fraction, and the number of orifices in the distributor, but almost entirely independent on where we put these orifices or of the geometry of the plastic particles we put in there. Similarly for the defluidization, which again we need to minimize in order to make sure that our systems last a long time and process the plastic waste efficiently. Just like the other one, very strongly dependent on gas velocity, plastic fraction, and the number of orifices in our distributor plate, but almost entirely independent of the size of the orifices and the geometry of the plastics we use. As for the next work that we're going to do, we're going to look at phase-changing materials with PEPT, which is going to involve designing some novel algorithms. We're going to create a new kind of synergistic positron emission particle tracking / positron emission tomography technique that will allow us to actually get deeper insight into these plastics as they go from a solid material, from a solid particle to a liquid to a volatilized gas, and then leave the system. So we can get real insight into every part of this system. And finally, we're going beyond empirical modeling. So we've proved rather emphatically that the empirical models that we as chemical engineers are rather comfortable using with these systems are simply not doing the job in these real commercial cases. So instead, we're going to move to numerical models, so computer simulations, which we can vigorously validate using PEPT data, and then ultimately also integrate the chemical kinetics so that we can model the whole process from start to finish. So the last couple of things I wanted to mention was the team working on this project. So Dominic Werner, who's funded by the Global Challenges Research Fund, has put an awful lot of legwork into producing these simulations and working with the PEPT data. Then we have Leonard Nikushan and Matthew Herold, who are working with us to produce the next generation of PEPT algorithms that we can use to process this data. Finally, a quick word about my funders. So thanks to all of these guys who have supported us extremely strongly with these projects. And that is that. If you have any questions at all, I am very glad to answer them, especially if there's anything that's piqued your interest. I'm more than willing to expand upon it. If you're interested in the PEPT technique itself, if you've got a system that you might like to see the internal dynamics of, then again, very keen to chat about that. And we as a group are always open to exciting new collaborations. The very, very final thing is we've got a new funded project looking at this plastic recycling starting in the new year. We've got a 2-year postdoc opportunity. We've got a 3.5-year PhD opportunity, and we're looking for some exceptional candidates to join us on this. So if you are somebody who's exceptional or you know somebody exceptional, do feel free to get in touch with me via email or any other means. So thank you very much for listening. I'll throw the floor open to any questions that you may have.
Thanks, Kit, for a great presentation. I'll remind our audience that you can type in your questions in the GoToWebinar toolbar, and I'll be reading those to Kit. While we're waiting for those to come in, I did have a question myself. So going back to talking about the fluidized beds, what is the gas composition of the so-called air that you use to make it fluidized?
It's actually an unbelievably simple system, and the simplicity of the system is actually one of its strengths. Let's do it. I can answer very quickly. I didn't really need a diagram. It's just pure nitrogen. So one of the amazing things about the system and the way it works is there are no catalysts. There is nothing that it's being fluidized with other than pure nitrogen. It's an extremely simple process where you just have these very fine but very durable sand particles and temperature. So the idea is to make it as simple as possible so you don't need any infrastructure to it, so that you can take this pretty much anywhere in the world as long as they've got a decent supply of nitrogen and you can set up one of these plants.
What's the energy requirement for this? I'm sort of thinking that maybe you could run this off of solar power or wind power or something like that.
Oh, you don't actually need to. That's one of the main things about it, is that you need a little bit of some kind of fuel, diesel or something like that to actually get it kicked off. But once the process is started, it's actually one of the fractions that you get out of it is a light hydrocarbon gas, and you can then burn that gas to power it. So after your initial startup, it powers itself.
That is really cool. It's sort of self-sustaining.
Exactly. So this is why I'm sort of heavily invested my research into looking at this, because I think it really is an amazing technology. And if we can just iron out the last few bugs in it, then it really could make a huge difference to the world.
So I've stolen this question from a popular radio show called Science Friday in the States. So if you're given a blank check, what would be like your first go-to research and like the big push for this?
Ooh, that is a very good question. A very, very good question. I think, if I'm perfectly honest, we've got huge investment with this company already. So money, ironically, is not the problem here. It is simply the time. It is simply that it takes time for us to actually perform this research and get the understanding that we need. So if I had my blank check, what I'd probably do is hire 100 graduate students and just get them all to work on this full time so that we can get the answers we need quicker, maybe build a second PEPT facility. But I think the sad reality is it's just a case of improving our understanding, which finance can only help so far.
So some questions from our online audience. What do you think this maybe become a commercial viability technology? 5 years, 10 years, 15 years?
Well, they're really quite ambitious, actually. So their goal is to have something like 27 of these machines out and functioning by the year 2027. So they've got quite an ambitious game plan. The first sort of commercial one is actually coming online in Scotland in the next few years. But at the moment, they're not selling them, they're just leasing them out and running them so that if anything goes wrong, they can come along quickly and fix it. So I would say, realistically speaking, 7 to 10 years, this should be ready. And certainly that's my research goal, is to, in the next couple of years, to have a fully working numerical model of the hydrodynamics. 2 years after that, have a fully integrated model with the chemical kinetics. A year after that, to have an actual complete process model for it. And then it's just a case of optimizing this process model and then rolling that out into the real machine. So I don't think it's that unrealistic.
What do you feel would be the cost and overall time frame for a city or a location interested in bringing such a solution to their location?
It's of the order of $1 million. I speak to the CEO. He's always very cagey when I ask him exactly what one of these costs. But the approach we're taking with this generally at the moment is actually that we Recycling Technologies, I wish I had shares in them. Sadly, it's not a we, it's a they. Will actually own the machine, and then the client will make profit by selling the product that they get out of the other end.
Any plans to come online in the US?
Oh, if we can find interested investors, absolutely. The ultimate goal of this is to make it truly global. So, being a British company, they're starting specifically in the UK and in Europe. But the ultimate plan is to have effectively one of these for every major state or city in the world, so that you can just, as soon as you've got your plastic waste, you can turn it straight back into something usable.
I haven't seen any more questions come in. So what final thoughts would you like to leave us with?
Oh, gosh, you hit me with the difficult ones here. Final thoughts are quite simply that, who's in our audience at the moment? Are we chemical engineers, mechanical engineers? What kind of people are we talking to largely?
I'll let the audience respond with their field of interest.
So it's okay, I'll give something generic then, but I think it...
I know in general we have some students and some government members, environmental engineers.
So the one thing that really strikes me about this process, this company, is that 10 years ago this company didn't exist. They're an absolute startup. It was one man with a very, very strong idea, and in a few years that's grown to a company employing 150 people, with millions and millions of pounds of research funding and people from the universities like Birmingham, like Surrey, working on it to help push it towards being a commercial reality. So I suppose the message I'd like to get across is, if you have any fantastic ideas that you're not sure about, or that you think, well, I think it would be great, but I couldn't necessarily get the investment, it would be to give it a shot, and just, you might be amazed how far it can go.
Great words of encouragement. So thank you for joining us, and feel free to reach out to Kit if any of these topics piqued your interest. And I will officially end the webinar now.
Thank you very much.